Alright, so answer B2 now. B2 is a question coming from chemical kinetics, okay? It's coming from a past, this is a past paper question. So sulfonyl chloride is a colorless corrosive liquid whose vapor decomposes in a reaction to sulfur dioxide and chlorine. So we've been given the equation for us. So what are we asked now? We're given the rate constant is 2.20 times 10 to the power negative 5 second negative. Okay, what is the order of the reaction? Okay, so there's a shortcut route that we go by, but well, by just looking at the units here, whenever you see a second negative alone, the order of the reaction is first order. Okay, nothing more, nothing less. um, think of since there are a few orders, so in case you forget, the formula we use is m raised to the power 1 minus n, and then second negative. So looking at the this formula helps us to find the units for the k. So whenever you see a k without an m, it implies the value of n was 0, or it's actually 1, so that it gives us 0. So n represents the order of the reaction. So if you put a 1 there, you'd actually see that you won't remain with second negative, which verifies our answer to be the first order. What is the half-life? So each order, 0, first, and second, they've got their own half-life formulas. Okay, so for first order, it's something very simple. It's just a natural log of 2 over the constant k. The half-life doesn't depend on the concentration. So natural log of 2 in this case divided by the rate constant k, 2.20 times 10 to the power negative 5 second negative. So this second negative, this would end up becoming time. Okay, so grab your calculator and perform that calculation. Okay, so you should get something closer to 31,500 seconds. Okay, so natural log of 2 in some textbooks says this is the same as 0.693, so no difference. And then the next one, how long, and that's in hours, would it take for 50% of that sulfonyl chloride to decompose? So 50%, it means half of it, right? How long will that take to decompose into its half? What do we do for such a question? So we're still interested in the time, right? So the equation for the first order, the integrated equation, is natural log of the final concentration is equal to negative kT plus the natural log of the initial concentration. By the way, if you want to learn more in details about the integrated ratios, because this is where this question is more focused on, or actually even the full topic, in the description below there's information on how you can access the full topic videos under chemical kinetics and some more chemistry topics. Okay, let's get back into it. So we've got the equation for this is the integrated ratio for the first order reaction, and then we are told 50% is what we are dealing with, right? So how can we handle it? How do we answer it? So what a piece of information have been given? So time has been is what we need to calculate. K is given in the question. Now we can come up with something to help us for 50% there for the final and the initial concentration. Okay, now we can come up with certain values to just help us. Okay, so let's say initially the initial is 100%, the half is 50%, right? So 100%, of course, 100 divided by 100 is 1, and then 50, that's like 0.5. So imagine you started with 1. So the equation would be natural log of 1 is equal to negative k, that's 2.20, times 10 to the power negative 5. Now adding a negative 1 there, okay. Well, let me take this to the board so that we answer properly. Okay, so I'll just do a question there. I'm going to go back to our board. Okay. Okay, so more space now, right? So the equation is natural log of the final concentration is equal to negative Kt plus the natural log of the initial concentration. So we're saying let our final be 0.5. That's what you expect if 50% of 1 would have gone. And then negative k, our k is 2.20 times 10 to the power negative 5, and then t plus natural log of the initial, let's say 1 in this case. Okay, so what do we remain with? We have natural log of 0.5, okay, on the left, and then we have negative 2.20 times 10 to the power negative 5 t. So natural log of 1, of course, we know is 0, so that part will just disappear. And then to find t, how do we find our t? Our t is going to be equal to, so we have to basically make t the subject by dividing by the constant k, right? So that's natural log of 0.5 divided by negative 2.20 times 10 to the power negative 5, okay, by making that guy the subject of the formula. And so our t, which is our time, natural log of 0.5 is the same as natural log of half is the same as 1 over 2, right? So now half is the same as 2 to the power negative 1, and that becomes negative natural log of 2, which is just negative 0.693. Anyway, calculators are allowed, so you can still just perform it. Just wanted to show that the sign is going to end up becoming positive. Okay, so dividing the two values would end up with a positive value. So our time in seconds is 1,000 506.69 seconds. Okay, and then we can convert to an hour. We know that in an hour we've got 3,600 seconds, so divide 3,600 seconds, or in a more organized manner, let's do this. Let's move this value a little bit. Let's do this. The value we have, 506.69 seconds multiplied by 1 hour. 1 hour as 3,600 seconds. So the seconds will just cancel, and then you end up dividing by 3,600. Since the question is requiring us to give answer in hours. Okay. end up with 8.75 hours. Okay, so that's how you handle C there. Now for D, what time in hours does it take for 25% of that to remain? This is now where you have to think smarter. So you have 100% at start. Now you're told what time in hours does it take for 25% to remain. 25% to remain. So 25% is like a final. So same process. That's a 1 divided by 100 is a 1. 25 divided by 100 is 0.25. So this is our initial, that's our final. Okay, so this is still a first order reaction, so the same equation applies. So feel very free to pause the video and just try that one out. So natural log of the final is equal to a minus kt plus natural log of the initial concentration. So the final is 0.25 minus kt, that's negative 2.20 times 10 to the power negative 5, that's our given rate constant in the question, and then times what we're trying to find, plus natural log of initial, which is a 1, that's still a 0, not important, stop here, and then natural log of 0.25 can be divided by negative 2.20 times 10 to the power negative 5 to give us time in seconds. So our time in seconds is basically equivalent to, so it will take longer, 63,013.38 seconds. Of course you want to divide by 3,600 to get the answer in hours as requested by the question. So therefore divide by 3,600 and then we end up with 17.5 hours. Makes sense, right? Now we're done. So let's see what E is asking us to do. So we didn't actually get E. So for E, if a temperature is increased from that, the value of K increases by a factor of 4. What is the activation energy of the reaction? So this is now the Arrhenius equation. We're talking about moving from temperature 1 to temperature 2, and then we are told K1 is increased by a factor of 4. So that's 4K2. Okay. So let's write down the equation. So the Arrhenius equation, let's just create some enough space here. Okay. So the Arrhenius equation, as we know it, is natural log of K2 over K1 is equal to negative, or just say EA over R1 over T2. In fact, if you don't want to add the negative, you start with T1. If you want to add the negative, you start with a T2, so start with T1. Okay, doesn't really matter. Okay, so just ensure that you are very careful with the signs. Okay, so the temperatures here are supposed to be in kelvins, so you'd want to add a 273.15 to both. Okay, so for the temperatures, add 273.15 to both. So my T1, after adding 273.15, 593.15, and then my T2 is 693.15 Kelvin. Okay, so natural log over K2, K1, these are in the ratio of, we said K2 is equal to, in fact we're told the value of K, so K1, the value of K will increase by a factor of 4, so it will be 4 times the first one. That's our K2. Okay, so that implies if K1 is 1, your K2 will be 4. So let's say 4 of 1. So the K1, which was the initial one, which was the initial K value, has increased by a factor of 4, so it becomes 4, which is 4 over 1. Now I'm trying to find the activation energy, which is represented by EA. Our rate constant that we use here is the 8.3145 value. Okay, so 8.3145 joules more negative Kelvin negative, implying that the temperature should be in kelvins. Now T1 is 593.15, and then T2 is 693.15. Okay, so at this point we can see that the only thing that is missing is the activation energy that we are asked to calculate. Okay, so we can see what we can do now. Natural log of 4, activation energy 8.3145. Okay, and in the brackets we have got 1 over 593 minus 1 over 693.15. Okay, so what do we do? If we cross and multiply at this point, what are we going to have? So natural log of 4 will multiply with this part, so we'll have natural log of 4 multiplied by 8.3145, and then is equal to the activation energy. When you subtract this and that part, it gives you 2.43225 times 10 to the power negative 4. Okay, of course that's Kelvin negative. Actually it becomes K positive. Okay, or if you're interested in keeping track of the units, and we're interested in to make our activation energy a subject, so we divide both sides by 2.3225 times 10 to the power negative 4 on both ends. Okay, so this part and that part, and so our activation energy becomes 8.3145 multiplied by natural log of 4 divided by 2.432225 times 10 to the power negative 4. So my activation energy that I'm getting is 47389.637 joules more inverse there. Okay, so what's our value? If you want to take to scientific notation, that would be 4.739 times 10 to the power 4 joules per mole. If you want, you can take it to kilojoules. Okay, that would mean you get cancel out these three, so that would be 47 kilojoules per mole. Depends on the units that are required, but there is no specification in the question, and you want to keep up to three significant figures. You want to say 47.4 kilojoules per mole. Okay, that's how you do handle E. And then finally, the last one under this question is where they want you to give want you to study the rate constant in comparison to the rate constant units in comparison to the order of the reaction. So I gave you a shortcut. I said m raised to the power 1 minus n second negative. This gives you the units. So for the first one, the fed order, if you substitute, it's clear what you'd actually end up with. Okay, so of course the units of based on what they're saying or what they're using in the question, we can break out down the molar into mole, okay, 1 minus n, and then also liter 1 minus n, and then second negative. So for a third order, if you try to substitute a 3, you'd basically get what they got there. They've actually given an example. Now this is a question that we handled in the earlier in the question. So second negative, without even wasting much of your time, if you plug in a 1 where there's n, you just remain with that part. So this is first order. For a 0 order, if you plug in a 0 and a 0, it will end up with so it would be more 1, liter 1, and then second negative. So you can just remove the ones, so it's just something like more dot so that would be a liter, and then what? Second negative. So doesn't actually make sense that way. This is supposed to be more per liter. I believe that was supposed to be the case as well for that part. Okay, more per liter second negative. So it's a product there. And then for the last one, this is negative 1. So how can we get a negative 1 for the m? How can we get a negative 1? So 1 minus n, for it to be equal to negative 1, 1 plus 1 is equal to n, so n is equal to 2. So that gives us a second order, right? So second order. And for sure, if you plug in 2, it's supposed to be 2, that would be more negative, and then the liter would be negative. If it goes to the top, it would just be positive. And yeah, this is one matches up. So basically, this is how you fill in this table. Don't forget the simple formula: molar concentration 1 minus n, second negative. N represents the order of the reaction. Okay, so that's it for this question, and we are done with this question B2.